the abstraction, address spaces. So we will gonna skip two further scheduler algorithm because it is in order to understand that we need to understand how memory works deeply and concurrency as well. We will gonna go back to those two chapters, but for now we will gonna discuss the basics of virtualizing memory. The abstraction, address spaces. In the early days, building computer systems was easy. Why, you ask? Because users didn't expect much. It is those darned users with their expectations of ease of use, high performance, reliability, etc., that really have led to all these headaches. Next time you meet one of those computer users, thank them for all the problems they have caused. Early systems, from the perspective of memory, early systems didn't provide much of an abstraction to users. Basically, the physical memory of the machine looks something like what you see in figure 13.1. So these are the early computers. You see, you have operating systems with code data at the start of the memory. And then this is all the current program. The OS was a set of routines, a library, really, that sat in memory, starting at physical address 0 in this example. So this OS is just a library, or a set of routines communicated to by memory. So we will discuss routines further later. And there would be one running program, a process that currently sat in physical memory, starting at physical address 64 kilobytes in this example, and used the rest of memory. So that's the early computer. You have one operating systems and one program or process. There were few illusions here, and the user didn't expect much from the OS. Life was sure easy for OS developers in those days, wasn't it? Multi-programming and time sharing. After a time, because machines were expensive, people began to share machines more effectively. Thus, the era of multi-programming was born. So because people needs to make those expensive resources more efficiently, the era of multi-programming was born, just like we discussed in the previous chapter, where some I/O, or once the process are doing I/O, you can then take advantage of CPU in another process, in which multiple processes were ready to run at a given time, and the OS would switch between them. For example, when one decided to perform an I/O, doing so increased the effective utilization of the CPU. Such increases in efficiency were particularly important in those days, where each machine cost hundreds of thousands or even millions of dollars. Soon enough, however, people began demanding more of machines, and the era of time sharing was born. So after multi-programming, the era of time sharing was born. Specifically, many realized the limitations of batch computing, particularly on programmers themselves. So the era of multi-programming is batch computing, in which the OS switch between processes or program. But now, in the era of time sharing, since that produced more headache to programmers and the users, the time sharing was invented. These programmers who were tired of long and hence ineffective program debug cycles. So because those multi-programming requires a lot of program debug cycles, a time sharing concept was born. The notion of interactivity became important, as many users might be concurrently using a machine, each waiting for or hoping a timely response from their currently executing task. So before, during multi-programming, it's not a lot of users that is in front of their computer that interacting them. In the era of time sharing, there is a lot, or people, computer becomes more democratized, which allows them to use it daily. That's why an interactivity, or the response time, which we discussed in the previous video, became important. One way to implement time sharing, that would be to run one process for a short time, giving it full access to all memory, like in figure 13. Point 1, so here, then stop it. Save all of its state to some kind of disk, including all of physical memory. So one way, or the first way we introduce to implement this time sharing, is to run one process for a short time and giving full access to memory like this. So the process monopolize memory, and then stop it, save all of its state to some kind of disk. So this 64 to something, it's huge, it's actually huge or larger than the OS. So when you save that in memory, especially that time, when you save that in disk, especially that time when saving disk is expensive, it took a lot for you to do that. So load some other processes state, run in for save all of its state to some kind of disk, including all of physical memory. So all of this, load some other processes state, run it for a while, and thus implement some kind of CRUD sharing of the machine. So after you save that to the disk, you'd now load some other program here, since you can now delete that. You already saved the state in the memory to the disk. You can now load another program. Unfortunately, this approach has big problem. It is way too slow, particularly as memory grows. While saving and restoring register level state, the PC general purpose registers, etc. is relatively fast. Saving the entire contents of memory to disk is brutally non-performant. So saving the program counter, like the previous state where you stop in the code, like and the registers are cheap when it comes to saving the disk. But saving this entire memory, especially the code is usually larger there. The code, the heap, the stock is non-performant. Thus, what we'd rather do is leave processes in memory while switching between them. So instead of that, removing this entire thing or code in memory, we'd rather keep it alive and then just switching between process. So as you can see here in the next diagram, allowing the OS to implement time sharing efficiently. So the OS are the one doing the time sharing. So as you can see, we have a pre-data, process C, process B, process A. So you can switch between them, keeping those memory on the instead of saving and that onto the disk, you save all of that in memory and you just switch in memory. So basically, your entire operation is entirely on memory, the address space. However, we have to keep those pesky users in mind, and doing so requires the OS to create an easy-to-use abstraction of physical memory. We call this abstraction the address space, and it is the running program view of memory in the city, in the system rather. So the reason why virtualizing memory were created is because the users or the program, the programmers and the users needs an interactivity. They want something easy to use. Therefore, this address space was created, and this address space is actually the running program's view of memory in the system. It's just a program view of the memory of the system. It's not the actual physical memory, it's just the program or the user processes view, and the OS or and the hardware cooperate later to then convert that to an actual physical memory. So this is where the virtualization of memory came from. The address space of a process contains all of the memory state of the running program. So this address space of the process contains all the more memory state of the running program. So assuming that process, a running program is currently running in the memory, this address space, because that process would not be able to be to run if there is no memory. So those running program has all of its memory state in that address space. For example, the code of the program, the instructions, have to live in memory somewhere for it, to have a life. It has to be in memory somewhere, and thus they are in the address space. Kind of like in the world, right? Kind of a lot of similarities with our memories. We can be alive if there's no memories. Our mind can be alive if it can't have memory, because it can have attention. It can't recall the past, the future. It can think in the future, etc. The program, while it's running, uses a stack to keep track of where it is in the function called chain, as well as to allocate local variables and pass parameters and return values to and from routines. So routines is actually a call from memory to the OS to allocate some memory. Now, while this program is running in the memory, it actually uses stack, and these stack are actually managed by the OS. This stack keep track of where that program is in the function execution, as well as if the stack needs to here. Sorry, we don't have a diagram. If the stack needs to expand, the OS will allocate more memory. It's really depend on the local variables here, local variables and pass parameters and return values to and from routines. Because in this stack is actually how the OS will return that depending on the instruction of the code. Because sometimes your code accept, for example, some data values, so the OS are actually transferring that to your disk or to the actual disk. Let's say you do an input or output, or to a memory, or let's say you want to calculate some infinite loop. The OS are the bridge for it to be communicated to the processor. But then again, it provides stock for that memory to virtualize this request. Now, let's say your request becomes so large that the stock or the address space is not available, then the OS will reject your request. Finally, the heap is used for dynamically allocated user managed memory, such as that you might receive from a call to malloc in C or new in an object-oriented language such as C++ or Java. So a heap is a user used for dynamically allocated. So this heap is not managed by your OS. It is managed by the programmer or the user or the processes using a call to malloc. So this malloc is a routine that taps into the OS. It's not a system call, but rather a routine that allows the compiler to, or OS, compiler to be able to talk to the OS to allocate more memory to this process. And then while it's allocating this memory, it also allocating the a memory in the actual physical address, not just in address space. Of course, there are other things in there too, like statistically initialized variables. So there's also statistically initialized variables. I think this is where you are able to avoid some memory problems, but this is rare. It really depends on the language. But for now, let's just assume that those three components, code, stock, and heap, are the um, memory data requirements of our process. Now, in the example in figure 13.3, where's the page 4? Let's see the 13.3. Where's the 13.3? Oh my goodness, I forgot. So in the example, in the figure 13, we have a tiny address, only 16 kilobytes. The program code lives at the top of the address space, starting at 0 in this example, and is packed into the first kilobyte. I think we need to have this diagram just a moment. There you go. And I think I actually deleted this. There you go. So here, in the example in figure 13.3 here, we have a tiny address space, only 16 kilobytes all. The program lives at the top of the address space, so that's the usual position of the program code. Let me change the screenshot. The program code lives at the top of the address space, starting at 0 in this example, and is packed into the first 1 kilobyte of the address space. Code is static and thus easy to place in memory. So this program code is static. It means that, like a static variables, when you say static, it doesn't change. Unlike this heap, it could change depending on the user allocated memory, but for the program code itself, it doesn't change. The stock could change depending on the input of the user, but this heap also depends on the program codes. So this code is static. Code is static and thus easy to place in memory, so we can place it at the top of the address space and know that it won't need any more space as the program runs. So that's the difference. As the time goes, just like in the OS scheduler, you have a different behavior for this memory, like for this heap. As the program runs with respect to time, it could go larger, and it could be more than this allocated by the OS, which could crash this program or process. So here, if grows negatively, the stock segment contains local variables, arguments to routines, return values, etc. So arguments to routines, return values, provided by the OS to communicate back to memory what it has been done. And then the heap segment contains malloc data, dynamic data structures if grows positively. So the reason why they are positioned this way, so that they won't interfere each other. Next, we have two regions of the address space that may grow and shrink while the programs runs. Those are the heap at the top and the stock at the bottom. We place them like this because each wishes to be able to grow, and by putting them at opposite end of the address space, we can allow such growth. They just have to grow in opposite directions. The heap thus starts just after the code at 1 kilobyte here and grows downward, say when a user requests more memory via malloc. So when a user or the program requests via malloc, then this grows downwards. The stock starts at 16 kilobyte and grows upwards, say when a user make a procedure call. So that's the difference. When you call malloc, it's a user it's a code. Basically, the programmer does that. Well, when you're making procedure call, it really depends on the nature of your inputs on the program. It's not really a code that can be controlled by the programmer, but it depends by the input of the process over time. So it's more like managed by the OS. However, this placement of stock and heap is just a convention. You could arrange the address space in a different way if you'd like, as we'll see later. When multiple threads coexist in an address space. So these are just the convention, the usual way. But we can change this position whatever we like, as we will later see in the modern complex operating system where it has multiple threads in it. These processes are broken down in multiple sub-process, so that's multiple threads. No nice way to divide the address space like this works anymore. So that's just this. We're just starting with the basics. That's why we're describing how this early memory virtualization are actually implemented. Of course, when we describe the address space, what we're describing is the abstraction that the OS is providing to the running program. The program really isn't memory at physical address 0 through 16 kilobytes, just like here. Rather, it is loaded at some arbitrary physical address. So rather, it is loaded at some arbitrary physical addresses. So it's not the actual 0 through 16 kilobytes in physical memory. It's just loaded in arbitrary physical. It's illusion that this OS provided to make the program is easy to interact with it in the physical memory, right? For the programmer and the user of the program or the process to be easier, right? Example processes A, B, and C in figure 13.2. There you can see how each process is formed into memory at different addresses. So this is the real physical address. You have the 0 kilobytes as operating system, and you have from 128 kilobytes to 192 the process C, its codes, data, etc. And hence the problem, the crux, how to virtualize memory. How can the OS build this abstraction of a private, potentially large address space for multiple running processes, all sharing memory on top of a single physical memory? Again, how can the OS build this abstraction of a private, so it's private from each other, potentially large address space, but not too large that it exists the available physical memory for multiple running processes? Because again, we enable the time sharing because we don't want long user or programmer debug cycles, and at the same time we also want the user to be interactive because user are more the computer is more democratized, therefore a lot of users are in front of their computers, so you need to make it this interactive. How would you do that? How would you a potentially large address space for multiple running processes all sharing memory on top of a single physical memory? So that's the crux. When the OS does this, we say the OS is virtualizing memory because the running program thinks it is loaded into memory at a particular physical address, say 0, and has potentially very large address space like 32 bits or 64 bits. The reality is quite different. So it's just an example because we're trying to do simple math, but in reality program could be millibytes or gigabytes in desktop now. So when, for example, process A in figure 13.2 tries to perform a load at address 0, which we will call a virtual address, somehow the OS, in tandem with some hardware support, will have to make sure the load doesn't actually go to physical address 0, but rather to physical address 320 kilobyte, where A is loaded into memory. So the way the way to solve this virtualization of memory is that the OS and hardware have to work in such a way, um, in tandem, in such a way to virtualize and not actually put that in the actual 0, because it will override the OS. Therefore it will compromise the system, the whole system. And the OS is actually the most important program in the system. This is the key to virtualization of memory, which underlies every modern computer operating systems in the world. So it's easy for the programmer or the user to be able to calculate their size of their process. Let's say you start with 0 and then end in 32 kilobytes, although you're not actually on that physical memory. It's just easier for the user and programmer to do that, and you're able to do that using the cooperation of OS and hardware. One major goal of virtual memory or VM systems is transparency. The OS should implement virtual memory in a way that is invisible to the running program. So one goal, or to be able to achieve this goal by OS and hardware, is to make it transparent. But by transparent, we mean that this virtual memory is invisible to the program. Like, though the program knows that it puts it's easier for them, kind of like in about face, right? You know that you did your job well if you're able to be invisible, because the user just do or use your product in seamless way, in such joy. But when they notice your product, let's say you're writing, when you're reading a fiction, if they notice some obscure word during that, therefore you did not do the right thing. It's kind of the same here. That's one of our goals, transparency, in a way that it's invisible to the running program or the user. Thus, the program shouldn't be aware of the fact that memory is virtualized. Rather, the program behave as if it has own private physical memory. So you're kind of giving them an illusion that they have a private physical memory. Behind the scenes, the OS and hardware does all the work to multiplex memory among many different jobs. So, but in reality, the OS and hardware are working together to divide those physical memory to support multiple jobs among many different jobs, and hence implement the illusion. Another goal of VM is efficiency. The OS should strive to make virtualization as efficient as possible, both in terms of time, not making programs run much more slowly, and space, not using too much memory for structures needed to support virtualization. Another goal is time and space complexity. So you want the process to run faster, but at the same time not too much memory. So that's also one of the reason why we invented time sharing. After multi-programming is time sharing, you want interactivity because you want faster time, but you don't want that at the expense of too much memory. In implementing time-efficient virtualization, the OS will have to rely on hardware support, including hardware features such as TLBs, which we will learn about in due course. So to achieve this goal of time efficiency, uh, the OS actually use a TLB. So this TLB has the OS rely on some hardware support. So this is how you achieve the time efficiency. But how do you actually achieve the space efficiency? Finally, a third VM goal is protection. So TLBs also achieve that space efficiency, but more like a cause and effect of making it time efficient, if it makes sense. Finally, a third VM goal is protection. Of course, security. One of the advantage of virtualizing memory and hiding it from the inside or from the process is that you also provide this protection. The OS should make sure to protect processes from one another, as well as the OS itself from processes. So again, processes from one another, and then OS from these processes. When one We discussed this in CPU virtualization, right? But there is a way for there's a techniques as well that is different from CPU, that is using by the OS to protect itself from in terms of memory allocation by these processes. So in the previous videos, we discussed the CPU allocation by these processes. Now we will discuss how we protect the memory allocation for each of these processes, because again, in order to run interactive program by the user to be able to actually accomplish something, you need CPU and memory, and here we will discuss the virtualization of that. Finally, a third goal is protection. The OS should make sure to protect all from another from process. When one process performs a load, a store, or an instruction fetch by the code, it should not be able to access or affect in any way the memory contents of any other processes or the OS itself. That is, anything outside its address space. So the key here is that anything outside this address space. That's how this OS and hardware support that. They have their own private address space. In the next chapter, we'll focus our exploration on the basic mechanism needed to virtualize memory. So again, we will just like as we start with CPU, we will start with the lower level mechanism before we get into the higher level, such as policy. Including hardware and operating supports. We'll also investigate some of the more relevant policies that you'll encounter in operating systems, including how to manage free space and which pages to kick out of memory when you run low on space. Again, we'll also investigate some of the more relevant policies that you'll encounter in operating systems, including how to manage free space and which pages to kick out of memory when you run on low on spaces. So policy is more like an algorithm. I'll give you an example. So some algorithm are designed has cache. So it's separates two address space for most frequently used process and not most frequently, so that it could cache that, so that you could return those frequently used processes. So that make the use of memory more efficient. So some of the policies or algorithms are actually created by Jeff Dean by Google, which we will discuss in the future videos, but I'm gonna stop that for now. And which pages to kick out memory when you run low on space. We have seen the introduction of major OS subsystem virtual memory. So this is a major OS subsystem. Aside from the topic of concurrency, virtualizing CPU, this is one of its major concepts. The VM system is responsible for providing the illusion of a large, sparse, private address space to each running program. So remember, in the first OS, it's like a library. It runs one program per hardware. So how it is this OS and memory run one program per hardware, like per CPU and memory, right? You only have one software. So how it is able to run now multiple software in just one hardware. So this is the subsystem of an OS. Each virtual address space contains all of programs, instruction, and data, which key. So this virtual address space, private virtual address space, contains all of the programs, instructions, and data. So all of the programs, algorithm, and data are in this virtual address space. That's why it's able to run on its own, which can be referenced by the program via virtual addresses, which can be, let's say the other program needs to access that, it can access that using its virtual address space. The OS, with some serious hardware help, will take each of these virtual memory references and turn them into physical address. So we will discuss further that low-level mechanism, but basically it's not OS alone. Hardware helps it to reference those virtual references to the actual physical memory, which can be presented to the physical memory in order to fetch or update the desired information from memory, could be from CPU to the disk, etc. Right? So the OS will provide this service for many processes at once. So this service of virtualizing memory or providing private address, private CPU, or like unneeded CPU for each processes are provided by the OS for all the processes each at once, that allow us to use multiple software in just one hardware, making sure to protect programs from one another's, which again one of the goal of the OS, as well as protect the OS. The entire approach requires a great deal of mechanism, like lots of low-level machinery, as well as some critical policies to work. So this approach needs a lot of low-level mechanism. So we're gonna work more in the hardware part to be able to implement this virtualization for protection for multiple processes, and only some policies. We'll start from the bottom up, describing the critical mechanism first. So here's a little program, va.c, that prints out the location of the main routine. So these are mean. It's actually a routine where code lives. So a routine is an allocated memory where the code lives, or the process data lives. The value of a heap allocated value returned from malloc, and the location of an integer on the stack. Again, the value of a heap allocated value returned from malloc, and the location of an integer on the stack. So where is it, this integer? Located on that virtual address. Again, all of these are just this return values or just virtual address. So when run on a 64-bit Mac, we get the following: location of the code 0x1095. So from this you can see that the code comes from first in the address space. So that's just like the graph that we saw earlier, where the code is the first one, and then the heap, and then the stack. Then the heap and the stack is all the way at the other end of this large virtual address space. So as you can see, 0x1095, and then you have 0196, and at the other end you have the stack. All of these addresses are virtual and will be translated by the OS and hardware. So again, not just OS alone. A lot of level mechanism are done by the hardware to be able to execute this in order to fetch values from there through physical locations or on their physical memory. Interlude, memory API. So just like in CPU, we have this system calls that we use to actually access memory. We also have these memory APIs. In this interlude, we discuss the memory allocation interfaces in Unix system. So how do we allocate memory, or what API do we use in Unix system using C? So how to allocate and manage memory in Unix C programs. Understanding how to allocate and manage memory is critical and robust and reliable software. What interfaces are commonly used? What mistakes should be avoided? So when allocating this heap and stack for this private virtual address space, what are the APIs for that? What are the most common mistakes, right? What do we need to understand to manage the memory on our processes in our code? in building robust and reliable processes or software. Now, types of memory. For that, we need to discuss types of memory. In running a C program, there's two types of memory that are allocated. The first is called stock memory. So in a running C process, there are two types of memory that are allocated. The first is called stock memory, and the allocations of it are managed implicitly by compiler for you, by the OS. Actually, the compiler that's managed that, but there's also an OS, right? But it's not much. It's a kind of like low level mechanism, kind of like hardware part. So it's this stock, or those stock in the diagram we mentioned, is actually handled by compiler for you. For this reason, it is sometimes called automatic memory. So because of that, it's an automatic. You don't need to manage it. It also likely depends on the user input, just like this. You see location of an integer on the stock. So that integer are determined by the input to your processors and determined by the input of your user. Depending on how huge that integer data will be determined by the input of the system, and the compiler or this low level mechanism adjusts accordingly. And it's called automatic memory. Declaring memory on the stock in C is easy. For example, let's say you need some space in function func for an integer called x. So just like an integer we have earlier. So in x, right, the integer you put on that will depend. Actually, integer has occupies more bits than string. So those bits in actual are translated by the compiler in the actual physical memory. Those bits are generated using this in our code in X. So to declare such a piece of memory, you just do something like this. It's also related on how we think of programming language, because no one really codes using assembly code, right? Even operating system are coded in C. This is how we talk to the actual CPU or computer. We need a memory to talk to the CPU. We use programming language. It converted to assembly language, and then converted the assembly language to a kernel text or instruction done by our CPU. This is how it is. Okay, but it's an automatic memory. So the compiler does the rest, making sure to make space on the stock when you call into func. So when you call into func, when that process runs, it makes space whatever the input the user has done. So the compiler will do that. So that's the lower level mechanism. When you return from the function, the compiler deallocates the memory for you. So that's how it provides the low level mechanism to virtualize the physical memory, or to make the private address available for other memory. So one of the goals is is that the protection, of course, the ease of use that requires by the program, because it is virtualized. The program requires interactivity nowadays, so that low level mechanism solves that. So if you want some information to leave beyond the invocation, you had better not leave that information in the stock. Now, if you want those information to be preserved, not just on runtime, because usually we need to hit Control Save, right, for a program to invoke other system calls on the OS, such as saving in I/O. But let's say you're not doing that, you don't put the code in the stock because it will not be saved. So let's just go back on the goals that it solved. So here you have the private memory, because the low level mechanism handle it for you. The efficiency as well. So it's time and space efficient, because once you deallocate that, you're able to use that for other processes. So that's what this low level mechanism does. If you want information to live beyond call invocation, you had better not leave that information on the stock. Again, it is this need that long-lived memory that gets us to the second type of memory. So because of this long-lived memory, we now get to the second type of memory, which is the heap memory, where all allocations and deallocations are explicitly handled by you. So let's say you want to perceive some data on the memory to run. You do that via heap, not via stack, because the OS or the compiler and the OS, of course, will work to deallocate those stack. But for heap, you decide how long it will stay, because it's allocated by you, the programmer. A heavy responsibility, no doubt, and certainly the cause of many bugs. But if you're careful and pay attention, you will use such interface correctly without too much trouble. Here's an example of how one might allocate an integer on the heap. So let's say we want to allocate an integer again. So in X, so a couple of notes about this small code snippet. First, you might notice that both stack and heap allocations occur on this line. First, the compiler knows to make room for a pointer to an integer when it sees your declaration of said pointer, int x. So again, first you might notice that both stack and heap allocation occur on this line. So there's an stack and heap allocation that happens in just this line. First, the compiler knows to make room for a pointer to an integer. So here, the compiler have to know, the OS and compiler have to know that there's a pointer to an integer at the start here, asterisk x, when it sees your declaration of said int asterisk x. Subsequently, when the program calls malloc, so here int asterisk and then malloc, it requests space for an integer on the heap. So you tell the compiler to make room for a pointer for this, and then the program allocates or requests space. So inside this, you request space for an integer on the heap. So you have this stack at the bottom, right? You have the heap, so to contain this integer. The routine, so these are routine because we're accessing memory. We're using compiler, so we're not doing system call. We're not using compiler to be able to create this private virtual address to be able to talk to allocate memory for a process to the actual physical memory to achieve efficiency, to achieve protection, right? What's the last goal that we have? Transparency, right? So that's how we achieve that using the compiler. So we're not doing system call here. The routine returns the address of such an integer. So this routine with the OS and compiler, it will return the address of the virtual address created for that process. So as you can see, this OS and compiler work together to provide the address that the program will use to communicate to the OS, and then the compiler will then convert that to the actual physical memory to be able to execute some instructions. So the routine returns the address of such an integer upon success or null on failure. Upon success or null on failure. Then this return address is stored on the stack for use by the program. So this return address is returned on the stack for use by the program. So this return address now will be used by the program to essentially communicate to the compiler, since it's allocated that already, this stack, and the compiler and the OS allocated this memory. Let's say this program needs some new allocation of memory. It just need to use this address with the OS and the compiler to be able for them to convert it in physical memory. Because of its explicit nature and because of its more varied usage, heap memory presents more challenges to both users and systems. So because it's explicit, like you need to explicitly allocated instead of automatic memory or implicit. This presents more challenges for both users and the system. So this is cause of a lot of bugs. That's why we will discuss of the common errors we have on this. So the malloc call. So the malloc call is quite simple. You pass it a size asking for some room on the heap, and it either succeeds and gives you back a pointer to the newly allocated virtual address space, or fails and returns null. So it either returns you the pointer of the virtual address space or null. So that's the malloc call. So the malloc page shows what you need to do to use malloc. So type man malloc at the command line and you will see what you can do with malloc. So that's applicable for most Unix programs or operating systems. So here include stdlib.h void.malloc size underscore t size. So from this information, you can see that all you need to do is include the header file stdlib.h to use malloc. In fact, we don't really need to even do this, as the C library, which all C programs link with by default, has the code for malloc inside of it. Again, in fact, you don't really need to even do this, as the C library, which all C programs link with by default, has the code for malloc inside of it. So you don't actually need to include this, because most of the C library, which all C programs has or linked by default, has the code for malloc inside of this. Inside of it. So this stdlib.h are encoded inside this malloc allocation. So adding the header just lets the compiler check whether you are calling malloc correctly. So if you had this header stdlib, it has an additional test functionality that allows you to check whether you are calling malloc correctly, like passing the right number of arguments to it of the right type, like what based on the functions arguments required, are you passing the right the correct arguments, and the type, is it the integer and string? And then later we will realize that just because we're able to run a program once does not mean that we did the right thing, because again, there's a lot of heap allocation that could happen. So that's also where when people saying that it works before, that it's not now, because you forgot to include the enough arguments and the right time. So the memory could run that for a while and then suddenly stops because it leaks, there's not enough memory to run because the program just make way to run those processes. Now, the single parameter malloc takes is of type size, which simply describes how many bytes you need. So the single parameter malloc takes is of type size. So here we have a parameter type size, which simply describes how many bytes you need. So this will depends on the requested bytes for the program or data. However, most programmers do not type in a number here directly, such as 10. Indeed, it would be considered poor form to do so. Instead, various routines and macros are utilized. So again, routines and are a way for allocation of virtual private address using the OSN compiler low-level mechanism. It's not an actual system call, so you don't actually put the actual number here. Instead, various routines and macros are utilized. For example, to allocate space for a double precision floating point value, you simply do this. So to allocate a space for a double precision floating point value, simply do this. So double times asterisk d equals double asterisk malloc size of double. So wow, that's a lot of doubling. This invocation of malloc uses the size of operator to request the right amount of space. So you don't these routines automatically get the right amount of space based on your arguments and type of data in C. So this is generally thought of as a compile time operator. So again, aside from routine, it's a compile time operator because a lot of low-level mechanism by compiler is doing the work for you, meaning that the actual size is known at compile time. So the actual size are known by this routine instead of the developer knowing those little details. And thus a number, in this case 8 for a double, is substituted as the argument to malloc. So since the compiler is actually the one invoking this virtual request to the actual physical memory, and he also knows the conversion in compile time, such as in this case 8, it is substituted as the argument for this to allocate space for a double precision floating point. For this reason, size of is correctly thought of as an operator and not a function call. So for this reason, because it is compiled or known in compile time, the size of is known via routine and known via compile time. It is not. It is thought of as an operator, kind of like addition, multiplication, division, or the most basic principles of programming language. It's not a function where you can reuse the code, right? Not a function call. A function call would take place at runtime, so it's not like that. So you can also pass in the name of a variable and not just a type of size of. So not just a type of the variable or the size of, you can also pass in the name of the actual variable, but in some cases you may not get the desired results if you input the name, so be careful. For example, let's look at the following code snippet. Int times x equals to malloc 10 times size of, and then int parenthesis close printf, and what's this, present d slash n, etc. So in the first line we declared space for an array of 10 integers. So int times x equals to malloc 10 times size of. So those kind of like the first line we have, where we allocate a stock pointer for x as to the x and a heap for this malloc. So we are we've declared the space for an array of 10 integers. So we declared a malloc space of 10 integers, which is fine and dandy. However, when we use size of in the next line, here in printf, it returns a small value such as 4 on 32-bit machines or 8 on 64-bit machines. So it also depends on the machines that you have, whether it's 32-bit or 64-bit. So for 32-bit, it will return 4, and then 8 for 62-bit processor. So the reason is that in this case, size of things, we are simply asking how big a pointer to an integer is. So as you can see, we declare the name, right? We don't just declare the size of, but the system misthink it. I don't know if there's that word. Thought of it as the pointer. How big the pointer to an integer, not how much memory we have dynamically allocated. So it's talking about the pointer, kind of like the pointer on the stock, not the memory allocated via heap for that integer, right? So however, sometimes size of does work as you might expect, like this. Int x with a parameter 10 and then close semicolon, printf open parenthesis again, just like the second line that we have the size of earlier, but now we don't have malloc, right? So printf percentage d slash n comma size of parameter x colon. So in this case, there's enough static information for the compiler to know that 40 bytes have been allocated. So there's enough of static information. It's not a variable information that provides us this information for the compiler to know that 40 bytes have been allocated. Another place to be careful is with strings. When declaring space for a string, use the following idiom. So because again, we're trying to make sure that we don't get this mistake when allocating heap, because this is the usual bug So another place to be careful is with string. When declaring space for a string, use the following idiom. Malloc, open parenthesis strlen, parameter s plus 1, closing parenthesis, which gets the length of the string using the function strlen, and adds 1 to it in order to make room for the end of the string character, using size of may lead to trouble here. So for string, you have to use the idiom malloc strlen parameter s plus 1. You might also notice that malloc returns a pointer to type void. Doing so is just the way in C to pass back an address So again, you might also notice that malloc returns a pointer type void. Doing so is just the way in C to pass back an address and let the programmer decide what to do with it. So sometimes malloc returns a pointer, not a type void, not the virtual address. It's just a way in C to pass back an address and let the programmer decide what to do with it. So yeah, the compiler, though return this success or null, sometimes it just return the address. So it returns success and then the address, right? But sometimes it returns a pointer to the type void, which just provide an address. It's different than success and providing the virtual address or null, which basically failed. It allows the program to decide what to do with that type void or the provided address. So the programmer further helps out by using what is called a cast. In our example above, the programmer cast the return type of malloc to a pointer to a double. So again, the programmer further helps out by using what is called a cast. In our example above, programmer cast the return type of malloc to a pointer to a double. Again, in our example above, the programmer cast the return type of malloc to a pointer to a double. So there's a lot of topic we have to discuss. Let's see if we can finish this, guys. The program further helps out by using what is called a cast, so that program created by the programmer could help by using cast. In our example above, the programmer cast the return type of malloc to a pointer to a double. So here we have this double. So the cast actually helped that because it allows the compiler compute the value of the size and then return it to the program. So casting doesn't really accomplish anything other than tell the compiler and other programmers who might be reading your code, yeah, I know what I'm doing. By casting the result of malloc, the programmer is just giving some reassurance. The cast is not needed for the correctness. So it just provides the programmer reassurance that he has the private virtual address, but it's not needed to make sure that you did the actual or the right call, or I don't want to say call, routine. So the free call, as it turns out, allocating memory is the easy part of the equation. Knowing when, how, and even if to free memory is the hard part. To free heap memory that is no longer in use, programmers simply call free. So as a matter of fact, we have an entire chapter just for freeing space in memory. So in malloc, just like in other memory, the hard part is freeing it, not allocating it. So to free heap memory that is no longer in use, programmers simply call free. So see here int x malloc 10x, and after the code free x. The routine takes one argument, a pointer, returned by malloc. So so the routine of this free call, it takes one argument, which is the pointer that returned by the malloc. Remember the stock pointer that returned by the malloc? Sorry, this is different from the stock. It is a pointer to the address returned by the actual allocation of malloc. So since it is x, we initiate that equals to int asterisk s for the stock. We will have that as an argument for our free x. Thus, you might notice the size of the allocated region is not passed in by the user. Again, thus you might notice the size of the allocated region is not passed in by the user and must be tracked by the memory allocation library itself. So the size of that allocated malloc region is not passed in by the user, only the pointer, the return address pointer for that stock, and must that size of that, or this malloc 10 times size of, must be tracked by the memory allocation library itself. So that memory allocation library is actually the routine that talks to compiler. It's not a system call again, etc. Common errors. There are a number of common errors that arise in the use of malloc and free. All of these examples compile and run with a pip from the compiler. So all of these examples compile and run with the compiler. While compiling a C program is necessary to build a correct C program, it is far from sufficient, as you will learn, often the hard way. So just because you're able to successfully compile, because again, that's how we allocate a physical memory and the virtual address to a process. Just because you're able to compile that process doesn't mean it will work. Correct memory management has been such a problem. In fact, that many newer languages has support for automatic memory management. In such languages, while you call something akin to malloc to allocate free memory, usually new or something similar to allocate a new object. So again, when allocating a memory, you use malloc, right? But sometimes you use new. So again, another thing is that this malloc is actually an object, okay? Just like in object-oriented programming we discussed. You never have to call something to free space in some other languages. Rather, a garbage collector runs and figure out what memory you no longer have references to and frees it for you. So some programming languages have a garbage collector that figures out what memory you no longer have references, that process reference to that virtual addresses, and then freeze it for you rather than having you call free and then activate the routine and such. So forgetting to allocate memory. So this is one of the issue with allocating or with heap. Many routines expect memory to be allocated before you call them. So before you call the routine and the compiler, you need to allocate memory for them first. For example, the routine strcpy argument dst, src copies a string from a source pointer to a destination pointer. However, if you are not careful, you might also do this. Char asterisk src equals to string hello, quote hello, semicolon, char asterisk dst semicolon, oops, unallocated, and strcpy dst src semicolon segfault and die. When you run this code, it will likely lead to a segmentation fault. So because you forget to allocate memory for that, it will result to a segmentation fault, because how can you implement this code or data if you don't have memory for it, which is a fancy term for you did submit wrong with memory, you foolish programmer, and I am angry. In this case, the proper code may instead look like this. You could use strd app and make your life even easier. So as you can see, we have malloc here, but as you can see, strdup, where's the strdup here? So here, instead of char does src equals to quote hello and then char asterisk dst semicolon, we have now char asterisk dst equals to open parenthesis char asterisk close parenthesis malloc open parenthesis strlen parenthesis src plus 1 semicolon, which is the allocation for us to implement our code. So that's where many routines expect memory to be allocated before you call them. So before calling these the routines like strcpy, copying it dst comma src, you need to call malloc. You need to have a malloc code. So that's one of the errors, which is forgetting to do that. So in this case, the proper code may instead look like this, and then after the after the strlen argument src plus 1 and then strcpy and then argument dst comma src, it will work correctly. So tip, it compiled or it ran is not equal it is correct. So this is what I'm saying earlier. Just because a program compiled or even ran once or many times correctly does not mean the program is correct. Many events may have conspired to get you to a point where you believe it works. But then something changes and it stops. A common student reaction is to say or yell, but it worked before, and then blame the compiler, operating system, hardware, or even dare we say it, the professor. But the problem is usually right where you think it would be in your code. Get to work and debug it before you blame those other components of the system. Instead of blaming other components such as professor, hardware, operating system, compiler, try to blame your code first. So not allocating, another error, enough memory. A related error is not allocating enough memory, sometimes called a buffer overflow. So that's actually what a buffer overflow is you're not allocating enough of memory for the requested data or code. In the example above, a common error is to make almost enough room for the destination buffer. So here's the example. So it's too small because it's almost enough. Malloc, str, and src. As you can see here, we have +1 to cover that. That's the reason why we have 1. Oddly enough, depending on how malloc is implemented and many other details, this program will often run seemingly correctly. So depending on how malloc is implemented and other many details such as OS, memory, how you choose your memory, this program will still work often seemingly correctly. In some cases, when the string copy executes, which is this, when you call the routine, it writes 1 byte too far past the end of the allocated space because there's no +1, right? But in some cases, so it ran past that allocated space, which means it could run or it could write in adjacent page because not enough memory. But in some cases, this is harmless, perhaps overriding a variable that isn't used anymore. So sometimes it could override the variables that is lurking in the system, kind of like in node structures, that it isn't used anymore. In some cases, these overflows can be incredibly harmful and in fact are the source of many security vulnerabilities in the system. In other cases, the malloc library allocated a little other cases, the malloc library allocated a little extra space anyhow. So sometimes the malloc library does the work for you and it allocates memory. And thus, your program actually doesn't scribble on some other variable's value and works quite fine. In even other cases, the program will indeed fault and crash, and sometimes it could be harmful. So, forgetting to initialize allocated memory. With this error, so sometimes you allocate a memory using malloc, but you didn't actually uh, initialize it. Or in this case, you didn't call the routine, you didn't copy anything, you didn't make do with the memory provided to you. So with this error, you call malloc properly, but forget to fill in some values into your new allocated data type. So you have now this allocated data type, but you don't provide the value. So how could the function execute it? Don't do this. If you forget, your program will eventually encounter an initialized read. So that's actually the error we see in our program, an initialized read, where it reads from the heap some data of unknown value or null value. Who knows what might be in there? If you're lucky, some value such that the program still works like 0. If you're not lucky, something random and harmful. Forgetting to free memory. Another common error is known as memory leak, and it occurs when you forget to free memory. So another, the free with the argument pointer, when you forget that, it will be lurking in your memory unused, right? In long-running applications or systems such as the OS itself, this is a huge problem. So for long-running programs, long-running consumer of CPU, this is a problem. A slowly leaking memory eventually leads one to run out of memory. So slowly leaking here will eventually leads to run out of memory. Therefore, at which point a restart is required. So if your memory leak, a restart actually requires, because your process could not contain it anymore. So it's how the crashes happen. It's a memory leak because your memory could not take it anymore. So whenever you have that automatic shutdown problem, it's usually a memory where the memory could not take a process as well, right? It could be a CPU, but it's unlikely. Thus, in general, when you are done with a chunk of memory, you should make sure to free it. So when you're done with the memory of the process you provided, you should make sure to free it. Note that using a garbage collected language doesn't help here. If you still have a reference to some chunk of memory using your process, no garbage collector will ever free it, and thus memory leaks remain a problem even in modern languages. So even though garbage collector in modern languages, there's still this problem of memory leak. That's why you have this code, you run it, and then it crash your entire memory, because it may have that bug for that operating system of your cell phone. So that's why it could restart your phone. Now, if your operating system, which is the most important program, is not designed or has been leaked, it is likely that you will need to install OS, or you need to buy a new phone. But if it's handled by the OS correctly, it's just a program. Usually you just need to end that process and then download another program that don't have that leak problem of memory. So in some cases, it may seem like not calling free is reasonable. For example, your program is short-lived and will soon exit. In this case, when the process dies, the OS will clean up all of its allocated pages, and thus no memory leak will take place per se. So it's better for short-running programs. While this certainly works, it is probably a bad habit to develop. So be wary of choosing such strategy. Even if you can get away with not doing so, it's probably good to get in the habit of freeing each and every byte you explicitly allocate. So it is better to freeing byte you explicitly allocate using malloc. Freeing memory before you are done with it. Sometimes a program will free memory before it is finished running or using it. Such a mistake is called dangling pointer, and it is, as you can guess, is also a bad thing. The subsequent use can crash the program or overwrite valid memory. So it could crash the program, end it, or it overwrite valid memory, like you called free but then called malloc again to allocate something else, which then recycles the recent freed memory. So that's not enough, or freeing memory before the process actually are able to use it. Aside, why no memory is leaked once your process exits? When you write a short-lived program, you might allocate some space using malloc. The program runs and is about to complete. Is there need to call free a bunch of times just before exiting? While it seems wrong not to, no memory will be lost in any real sense. The reason is simple. There are really two levels of memory management in the system. So, the reason why short-lived memory is not that harmful is because there's two levels of memory management in the system. The first level of memory management is performed by the OS, which hands out memory to processes when they run and takes it back when processes exit or otherwise die. So kind of like in stock, it managed the stock, right? But for all processes, it actually reclaimed that because one of the OS goals is efficiency. The second level of management is within each process. So with the program itself. For example, within the heap, when you call malloc and free, you are creating a new space for value for that data type inside your process. Even if you fail to call free and thus leak memory in that heap or in your process, the operating system will reclaim all the memory of the process, including those pages for code, stock, and as relevant here, heap. So including that, not just the malloc which you erroneously created, which is also the heap, which is managed by the OS and the code. When the program is finished running, no matter what the state of your heap in your address space, the OS takes back all of those pages when the process dies, thus ensuring that no memory is lost despite the fact you didn't free it. Thus, for short-lived memory programs, leaking memory often does not cause any operational problems, though it may be considered poor form. So for short-lived, it actually does not have any operating system problem, though it may consider poor programming. So when you write a long-running server, such as a web server or the database management system which never exit, leak memory is much bigger issue and will eventually lead to a crash when the application runs out of memory. And of course, leaking memory is an even larger issue inside one particular program, which is the operating system itself. So as long as the operating system does not have this leak memory and your program is just a transient application, then you're good to go. Showing us once again, those who write the kernel code have the toughest job of all, freeing memory repeatedly. Programs also sometimes free memory more than once. This is known as the double free. So that's a common error as well with malloc. The result of doing so is undefined. As you can imagine, the memory allocation library might get confused and do all sorts of weird things. Crashes are a common outcome if you double free the memory. Calling free incorrectly, free expect you only to pass it one of the pointers you received from malloc earlier. So the free only expect you to an argument of x, which is the pointer for the stock which you received from malloc call, which you equate earlier. Thus, invalid frees are dangerous and of course should also be avoided. As you consider a lot ways to abuse memory, because of the frequent errors with memory, a whole ecosphere of tools have developed to help find such problems in your code. Check out both Purify and Valgrind. Both are excellent, helping you locate the source of your memory-related problems. Once you become accustomed to using these powerful tools, you will wonder how you survive without them. Underlying OS support. You might have noticed that we haven't been talking about system calls when discussing malloc and free. The reason for this is simple. They are not system calls, but rather library calls. Again, they are not system calls. It's a library call. Does the malloc library manage space within your virtual space? So this is the key. So there's a low-level malloc mechanism, and there's the malloc library, which manages space within your virtual address space. So this is how we virtualize memory. but itself is built on top of some system calls which call into the OS. So again, this library are built on top of a system call which then call to ask for more memory or release some back to the system. So it is on top of this, it allocates, this malloc library allocates memory as a virtual address for you, but it activates system calls because remember that's how we trap into the OS. One such system call is called BRK. So this is how the malloc library contact, which is used to change the location of the program's brick, the location of the end of the heap. So this BRK are actually used to change the location of the heap in the actual physical memory address. But again, malloc library virtualize it for you. This is how they work to virtualize the memory. So it takes one argument, the address of the new brick. So this BRK takes one argument, which is the address of the new brick, which is communicated to it via the malloc, and thus either increases or decreases the size of the heap based on whether the new brick is larger or smaller than the current brick. So it's the one which is increases the physical memory with whether it's larger or smaller. An additional core SBRK is past an increment but otherwise serves a similar purpose. So an SBRK, instead of passing as a program's brick, it is passed an increment but otherwise serve as a similar purpose, which is to increase the allocation for physical address for that malloc library as a virtual address. Note that you should never directly call either BRK or SBRK. They are used by the memory allocation library. If you try to use them, you will make something go horribly wrong. Stick to malloc and free instead. Finally, you can also obtain memory from the operating system via mmap call or system call. By passing the correct arguments, mmap can create an anonymous memory region within your program, a region which is not associated with any particular file but rather with swap space. So it's not associated with particular file but with swap space, something we'll discuss later in the future video in virtual memory. So this memory can also be treated like a heap and managed as such. So this swap space memory can also be treated as a heap and therefore be managed by programmer as such. Read the manual page of mmap for more details. So other calls, there are a few other calls the memory allocation library support. For example, calloc. So this is a system call as well, allocates memory and also zeroes it before returning. So it allocates and then zeroes it before returning. This prevents some errors where you assume that memory is zeroed and forget to initialize it yourself. The routine realloc or is a system call as well. So again, routine is a system call to the OS for it to talk into compiler and then to the kernel text. The routine realloc can also be useful when you allocated space for something, say an array, and then need to add something to it. The routine realloc, again the system called realloc, can be useful when you've allocated space for something like an array and then need to add something to it. So let's say you already have that in physical memory an array and you need to add to it. Realloc makes a new larger region of memory, copies the old region into it. So this is how you copy the process. So this is what virtual memory or library, virtual memory library calls to copy from one space to another virtual address space. Copies the old region into it and returns the pointer to the new region. So again, they have all the same characteristics. These routines or system call returns the pointer to the new address for the program to use when it's executing its process. For a cool modern paper on how to detect and correct many of these problems automatically, see Novark et al. This paper also contains nice summary of common problems and some neat ideas on how to fix them. So mechanisms, address translation. In developing the virtualization of the CPU, we focus on a general mechanism known as limited direct execution or LDE. The idea behind LDE is simple. For the most part, let the programmer run directly on the hardware. So that's the process of the LDE. As we see on the previous video, the program is directly interacting with the hardware. However, at certain key points in time, such as when a process issues a system call or a timer interrupt occurs, arrange so that the OS gets involved and make sure that right things happen. So this LDE makes sure that the OS and hardware is safe. The OS is using a system call, right? And the hardware using interrupt, such as a Control C or any interrupt, keyboard interrupt connected to the hardware that will allow us to interrupt that process or to make the system secure. Thus, the OS, with a little hardware support, try its best to get out of the way of the running program, but with restriction, right? To make that program able to run faster, to deliver an efficient virtualization. However, by interposing those critical points in time, the OS ensures that it maintains control over the hardware. So it maintains the control over the hardware using the system calls. Efficiently and control together are two of the main goals of any modern operating system for CPU. So in virtualizing memory, we will pursue a similar strategy, attaining both efficiency and control while providing the desired virtualization. So just like the technique we had with hardware, we will also do that with memory. Efficiency dictates, with CPU, just like our strategy with CPU, we will also discuss that with memory. Efficiency dictates that we make use of hardware support, which at first will be quite rudimentary. So that's like the interrupt. So we will also implement that in memory, just a few registers, but will grow to be fairly complex. So this hardware support in memory is at first quite rudimentary, using just a few registers, base and bound registers to remember it, and then moving to a fairly complex like TLBs, page table support, and so forth, as you will see. So these TLBs are the modern way we manage this virtual memory. This is how hardware help our OS to maintain efficiency and control. Control implies that OS ensures that no application is allowed to access any memory but its own, just like any process are not allowed to access the processor if it's a multiprocessor. Thus, to protect application from one another and the OS application, we will need help from the hardware here too, just like with OS. Finally, we will need a little more from the VM system in terms of flexibility, specifically with like for programs to be able to use their address spaces in whatever way they would like. So finally, we will need a little more from the VM system in terms of visibility. Specifically with like for programs to be able to use their address spaces in whatever they would like. So again, finally, we aside from efficiency and control, we need a little more from the VM system of the memory, which is flexibility. We want a private virtual spaces for each processes in whatever they would like, thus making the system easier to program. And thus we arrive at the refined crux: how to efficiently and flexibly virtualize memory. How can we build an efficient virtualization of memory? How to provide the flexibility needed by applications? How do we maintain control over which memory locations an application access and thus ensure the application memory accesses are properly restricted? How do we all this do this efficiently? Again, how can we build an efficient virtualization of memory? How do we provide the flexibility and privacy needed by applications? Let's say they want privacy, and then at other time they want access to other processes. How do we maintain control over which memory locations an application can access? How can we make sure that it doesn't access the 0 kilobytes, which is the actual location of memory? So the general technique we will use, which you can consider an addition to our general approach of limited direct execution, is something that is referred to as hardware-based address translation, or just address translation for short. So aside from malloc library call and limited direct execution help to virtualize memory, or to have this flexibility for processes, we have another criteria for virtualizing memory, which is the translation of virtual to address, which we call hardware-based address translation. With address translation, the hardware transforms each memory access, an instruction fetch, load or store, changing the virtual address provided by the instruction to a physical address. So the hardware actually transforms that memory access, which is the changing the virtual request from malloc to provided by the instruction of the code to the actual physical memory where the desired information is actually located. So that's another characteristics that we don't have with limited direct execution protocol. Thus, on each and every memory reference, an address translation is performed by the hardware. So you may think that it's done by the malloc or compiler. It's actually more on hardware side to redirect application memory references to their actual locations in memory. Of course, the hardware alone cannot virtualize memory, as it just provides the low-level mechanism for doing so efficiently. So just like before, we also need an OS. So the OS must get involved at key points to set up the hardware so that the correct translation take place. So at key points, an OS need to be there to set up the hardware and provide this correct translation from virtual to physical address. It must manage the memory, keeping track of which locations are free and which are in use. So it must know what are free, it must track it, and which are in use to be able to make this translation properly. That is not included in limited direct execution. And judiciously intervening to maintain control over how memory is used. So let's say that already that track memory, some process wants to access that, it needs to from time to time send null or failure or reject for that request. So that's how we receive those null when we request a bytes from non-contiguous memory, though we still have those part of memory all over the system, but since it's not contiguous, the OS rejects that. So once again, the goal of all of this is to create a beautiful illusion that the program has its own private memory where its own code and data reside. Behind that virtual reality lies the ugly physical truth that many programs are actually sharing memory at the same time, as the CPU or CPU switches between running one program and the next. Unfortunately, there's a hard truth that programs share memory at the same time as the CPU switches between them using context switch. Specifically, that is less than the size of physical memory. So specifically, these programs have less than the size of the physical memory. So if you have like 16 gig, you can expect that the program you can run on that is less than that. Finally, we will also assume that each address space is exactly the same. Don't worry if these assumptions sound unrealistic, we will relax them as we go, thus achieving a realistic virtualization of memory. So for now, we will describe each address space as the same or equal body. But just like before, when creating an algorithm, we will relax them as we go and provide a more realistic view of how the memory actually works. An example, so to understand better what we need to do to implement address translation and why we need such a mechanism, let's look at a simple example. Imagine there is a process whose address space is indicated in figure 15.1. What are we going to examine here is a shortcode sequence that loads a value from memory, increments it by 3, and then store the value back into memory. So imagine there is a process whose address space is indicated here, 15.1. What are we going to examine here is a shortcode sequence that loads a value from memory, increments it by 3, and then stores the value back into memory. So here, we increment it by 3, and then line of code we are interested in. It loads a value from memory here, which is the one we initiated, increments by 3, and stores the value back into memory. So it stores the value back. So you can imagine the C language representation of this code might look like this. So here, initialize 3000. So again, that stack again are created by our code. It's initiated like this. So you can put 4000 there, then the stack will become bigger depending on the size of the integer that you, or the strings or the data types or the value of the data types you allocated. So here, the compiler turns this line of code into assembly, which might look something like this in x86 assembly. So use objdump on Linux or OTOOL on a Mac to disassemble it. So as you can see here, this is the program code. 128 move 0x EAX. So we will discuss this further in the next video. So a process in its address space looks like this.